There is one RDS question that gets asked in almost every AWS interview, and a startling number of engineers get it wrong. The question is, what does multi-AZ give you? And the wrong answer, the one that comes out automatically, is it spreads the RAID load across two availability zones. It does not. The multi-AZ standby serves no traffic. You cannot read from it. You cannot query it. You cannot point a reporting tool at it. It sits there, fully provisioned, costing you exactly double doing nothing, until the primary fails, at which point it becomes the primary. That is its entire job. Multi-AZ is about availability. Read replicas are about scale. They are completely different features. They solve completely different problems, and the reason people confuse them is that both of them create a second copy of your database, so they look the same on an architecture diagram. They are not the same, and the person who can explain why they are different. Synchronous versus asynchronous replication, and what that means when things break, is demonstrating that they understand the database, not just the AWS console. 9 concepts. We will do failover properly, the backup story, the parameter groups that will surprise you, and the things that will page you at 3 in the morning. Let us draw the distinction sharply, because everything else depends on it. Multi-AZ, AWS keeps a standby in a different availability zone, and replication to it is synchronous. When you commit a write, RDS does not acknowledge it to your application until that write is durable on both the primary and the standby. Think about what that guarantees. If the primary dies right now, the standby has every committed transaction. 0 data loss. And think about what it costs. Every write now pays a network round trip across an availability zone before it returns, so your write latency goes up. You have traded write speed for durability, and that is a deliberate, correct trade for a system of record. A read replica is the opposite trade. Replication is asynchronous. The primary commits your write, tells your application it is done, and ships the change to the replica whenever it gets round to it. Your writes stay fast, no waiting, but the replica is behind. Milliseconds usually. Seconds under load. Minutes if something is badly wrong, and this is the part that hurts. And you can read from it, which is the whole point. You can have up to 15 of them spread across regions and point your dashboards and your reports at them. So, synchronous, invisible, 0 data loss, no reads. That is multi-AZ. Asynchronous, readable, lagging, scales your reads. That is a replica. One protects you from a failure. The other protects you from your own traffic. Most serious systems need both, and they are billed separately. Concept 1. What actually happens when the primary dies? Here is the mechanism, and it explains almost every failover surprise you will ever have. Your application does not connect to an IP address. It connects to an endpoint, a DNS name, something like myDB.abc123.assist1.rds.amazon.com. That name resolves to the current primary. When RDS fails over, it does not move anything and it does not tell your application. It simply repoints that DNS record at the standby. The standby, which has every committed transaction because replication was synchronous, is promoted and the name now resolves to it. Typically 60 to 120 seconds, and AWS does it automatically. Now, the consequences, and this is where teams get hurt. First, your application must reconnect. Every connection in your pool is pointing at a machine that is gone, and they will not heal themselves. They will sit there, holding dead sockets, throwing errors until something forces them to re-resolve. Second, and this is the classic, Java caches DNS. The JVM has historically cached DNS lookups forever, by default, which means your application will keep resolving to the OLD primary's IP address long after the failover completed. And you will sit there watching AWS tell you the failover succeeded while your application insists the database is down. Set network address.cache.ttl to something like 30 seconds. Third, failover is not free. It is a real, brief outage, and it is triggered by more than just a crash. An availability zone failure, yes, but also a storage failure, a patching operation, and the one that surprises everyone, changing the instance class. So test it. AWS gives you a reboot with failover button precisely so you can find out whether your application survives it before the night it happens for real. Concept 2. Scaling reads. and the lag that will bite you. Read replicas scale reads, and they do it well. Up to 15, cross-region if you want, each with its own endpoint, and you point your read-heavy work at them, dashboards, reports, analytics, search. And you can promote one to be a standalone database, which makes it a passable disaster recovery story across regions. But replication is asynchronous, and that means lag. And lag is not a performance problem. It is a correctness problem. And here is the bug that every team writes at least once. A user updates their profile. You write to the primary. The write succeeds. You redirect them to the profile page. That page does a read, and your load balancer sends it to a replica. The replica has not received the change yet, so the user sees their old profile immediately after saving it, and they are certain your application is broken. And they are right. This is called read your own writes, and it is one of the most common consistency bugs in production. And it is entirely self-inflicted by naive read routing. The fixes, in order of how much I like them: read from the primary for anything a user just wrote. The simplest fix, and usually the right one. A user's own data is a tiny fraction of your read traffic, so send it to the primary and stop worrying. Or route by staleness tolerance. Reports and dashboards can be 5 seconds behind and nobody cares, so those go to a replica. Anything in a user's own session goes to the primary. Or use a sticky session so a user who wrote is pinned to the primary for a while. What you must not do is what most teams do first. Send all reads to a replica because it is cheap. And discover this bug in production from a support ticket. And you must monitor the lag. CloudWatch publishes replica lag and alarm on it. Because under heavy write load, that lag will grow, and your read path is silently serving old data, and nothing is on fire. Concept 3. Backups, snapshots, and the difference that matters. Two different things, and people mix them up constantly. Automated backups. RDS takes a daily snapshot and continuously ships your transaction logs to S3. That combination is what gives you point-in-time recovery. You can restore to any second within your retention window, typically up to 35 days. So if someone runs a delete without a where clause at 10:14 this morning, you can restore to 10:13. That is the feature you are actually paying for. Two sharp edges. First, the retention window is configurable, and if you set it to 0, automated backups are disabled. No point-in-time recovery at all. And RDS will let you do that without much of a fight. Check it. Second, and this is the one that genuinely ruins people's day. When you delete the database instance, the automated backups are deleted with it. They are tied to the instance's lifecycle. Delete the instance, lose the ability to recover it. Manual snapshots are different. You take them, they live until you delete them, and they survive the instance being destroyed. So before any risky migration, take a manual snapshot. And the critical thing to understand about restores, which catches people out in incidents: a restore does not restore into your existing database. It creates a NEW instance with a NEW endpoint, which means your recovery is not just how long the restore takes. It is the restore plus repointing every application at a new endpoint, plus whatever DNS or config change that requires. If you have not practiced it, your recovery time objective is a number you invented. And the honest summary, your backups are not real until you have restored one. Everyone has backups. Far fewer have restores. Concept 4. The config layer nobody reads until it hurts. You do not get a shell on an RDS instance. There is no my.cnf, no PostgreSQL.conf that you can edit. All engine configuration goes through a parameter group, an AWS object holding your engine settings, and you attach it to the instance. The default parameter group cannot be modified, which is the first thing people trip over. You must create your own, even to change one value. Now the part that matters, and it is a real operational trap. Parameters come in two kinds. Dynamic parameters apply immediately. Static parameters require a reboot, and the instance will happily sit there in a state called pending reboot, telling you your change is applied while it continues running on the old value. So you change max connections, you see it in the console, you assume you are done, and you are not. The instance is still running the old number, and it will keep doing so until someone reboots it, possibly weeks later. possibly during an unrelated incident, and now your database behaves differently and nobody knows why. Check the parameter group status. If it says pending reboot, your change has not happened. And a few parameters actually worth knowing about max connections. On RDS, this is derived from a formula based on instance memory. So a smaller instance quietly allows fewer connections, which is why scaling down can suddenly break an application that was fine. Timeouts, query logging, slow query log from MySQL, the auto-explain module for Postgres, and these are how you find the bad query rather than guessing. And the one I would tell you to turn on before anything else, performance insights. It gives you a graph of database load broken down by wait event, and it will tell you in about 10 seconds whether you're blocked on CPU, or on I/O, or on locks, which is the question you're actually trying to answer at 3 in the morning. Concept 5. The storage trap, and it is a nasty one. This is one of the sharpest gotchas in RDS, and it produces an incident that looks completely inexplicable if you do not know about it. General purpose GP2 storage gives you IOPS in proportion to size, 3 IOPS per gigabyte. So 100 gigabyte volume gets 300 IOPS. That is not very much, but small volumes also get burst credits. They can spike up to 3,000 IOPS, drawing down a credit balance. And while those credits last, everything is fast and your database feels great. Then the credits run out, and your database does not fail. It does not throw an error. It just becomes, suddenly and permanently, 300 IOPS slow, and every query starts queuing behind disk I/O, and your application times out, and CPU looks fine, and memory looks fine, and nothing in your application changed. Teams lose entire days to this, because every instinct sends you looking at your own code. The tell is a CloudWatch metric called burst balance quietly heading towards 0. And if you are not watching it, you will never think to look. The options. Use GP3, which decouples IOPS from size and lets you provision them directly. And this is the same default now, and if you are still on GP2 you should ask why. Use provisioned IOPS EO1 or EO2 for genuinely IO-heavy workloads where you pay for guaranteed IOPS. Or simply over-provision the volume, because on GP2 a bigger disk is a faster disk, which is an absurd thing to have to know. And it is true. Also, storage auto-scaling will grow your volume when it fills, which is a genuinely good feature. But note it only ever grows. It never shrinks. You cannot reduce RDS storage, ever. The only way down is to dump and restore into a new instance, and people find that out at exactly the wrong moment. Concept 6. The failure that scales with your success. Every database connection costs memory on the server. On Postgres, each one is an entire operating system process, and that is not a small thing. So max connections is not a number you can simply raise. It is bounded by the memory of the instance, and RDS derives it from a formula for exactly that reason. Now think about how a modern application behaves. 20 pods, each with a Hikari CP pool of 10 connections, is 200 connections, and they are held open, whether or not they are doing anything. Now auto-scale to 50 pods under load and you have 500 connections. And you have exhausted the database's limit at precisely the moment you needed it most. That is the shape of the failure, and it is savage. Your database becomes unreachable exactly when traffic is highest, and the auto-scaler's response is to add more pods, which makes it worse. Worse still, serverless makes this acute, because 1,000 concurrent Lambda invocations means 1,000 attempts to connect, each one from a fresh execution environment with no pool to share. The answer is a connection pooler between your application and the database. RDS proxy is the managed one. It holds a warm pool, multiplexes many client connections onto few database connections, and this is a genuinely underrated feature. It can hold a client's request during a failover and replay it, so a failover becomes a pause rather than an error. PG Bouncer is the self-managed equivalent, and the sizing intuition that will win you an interview. Your database can handle far fewer connections than your application wants to open, and the correct fix is almost never to raise max connections. It is to open fewer. A connection that is idle in your pool is memory the database could have used for cache. Concept 7. Where the database actually lives. Your database goes in a private subnet, not a public one. It has no route to an internet gateway. It is reachable only from your application's security group, and the right way to express that is not an IP range. It is a security group reference. Allow inbound on 5432 from the application's security group. That way, any instance in that group can reach the database, and nothing else can, and it keeps working as instances come and go, which is exactly what we cover in the security groups episode, and it is the single most useful AWS networking idea. Now, the setting to be afraid of. RDS has a flag called publicly accessible. If it is on, your database gets a public IP address. And I want to be precise here because people overstate this. A public IP alone does not mean anyone can connect. Your security group still has to allow it. The disaster is the combination publicly accessible plus a security group that allows 5432 from 0.0.0.000. And that combination is not rare. People do it to debug something from their laptop, and it stays. There are databases on the internet right now with default ports and weak passwords because someone needed to check a table one afternoon in 2022. The rest, quickly, and none of it is optional. Encryption at rest with KMS. Turn it on at creation, because you cannot enable it on an existing instance. You have to snapshot, copy the snapshot with encryption, and restore, which is a migration, not a checkbox. Enforce TLS in transit and enforce it in the parameter group rather than trusting every client to ask for it. Use IAM database authentication or secrets manager with automatic rotation. So the password is not a string sitting in a config file that was committed to Git in 2019. And rotate. Actually rotate. Concept 8. Where the money actually goes. RDS is one of the most expensive things on a typical AWS bill, and the reasons are worth knowing before someone asks you why. Multi-AZ doubles your instance cost. You are paying full price for a standby that serves no traffic. That is not a ripoff. It is what zero data loss availability costs. But it does mean you should not switch it on for a development database that nobody would notice being down for an hour, and plenty of teams have it on everywhere because it was a checkbox and nobody thought about it. Each read replica is another full instance at full price. Storage is billed for what you provisioned, not what you used. And remember, it only grows, so a volume that auto-scaled to a terabyte during one bad week is a terabyte you are paying for forever. Provisioned IAPs are billed separately, and they are not cheap. Backups, storage up to your database size is free, beyond that you pay. And cross-AZ data transfer, which your multi-AZ synchronous replication is doing on every single write, is a line item people never anticipate. Where the savings are. Reserved instances or a savings plan will cut 30 to 60% off a steady workload. And if your production database is running on demand, you are simply donating money because it is the one workload you know for certain will still be there in a year. Right size, using performance insights rather than a guess. Stop your development databases outside working hours. Though note RDS will restart a stopped instance after 7 days, so you need automation. And GP3 instead of GP2, which is usually both cheaper and faster, which is a rare combination. Concept 9. The questions and the answers that land. 5 questions, and how to answer them well. 1. Multi-AZ versus read replica. Do not just say availability versus scale. Say why. Multi-AZ is synchronous, so zero data loss on failover, and the standby serves no traffic. A replica is asynchronous, so it lags, and lag is a correctness problem, not just a performance one. That distinction is the whole answer. 2. How do you scale reads? Read replicas, and then immediately read your own writes, unprompted, and explain how you would route around it. Volunteering the failure mode is what separates you. 3. How do you handle failover? It is a DNS change, so my application must reconnect, and I would set the JVM DNS TTL because the JVM caches forever by default and will keep hitting the dead priory. And I would test it with reboot with failover before it happens for real. 4. My database is slow. What do you check? Do not start guessing at queries. Say, performance insights first to see what it is waiting on. CPU, I/O, or locks. Then check burst balance, because if this is GP2 and the credits are gone, the database is I/O starved and nothing in the application changed. That answer says you have actually debugged one of these. 5. How do you handle 1,000 lambdas? RDS proxy. Because 1,000 concurrent invocations means 1,000 connection attempts, and Postgres spawns a process per connection. And the meta answer that will genuinely mark you out. Know that the standby serves nothing. It is the single most common thing people get wrong about RDS, and getting it right in the first 30 seconds tells the interviewer you have actually run this in production rather than read about it. Let us land it. Multi-AS availability, asynchronous standby, zero data loss, serving no traffic, costing you double. Read replicas are scale, asynchronous, readable, and always a little bit behind. And that lag is a correctness bug, not a performance one, which is why a user can save their profile and immediately see the old version. Read your own writes from the primary. Failover is a DNS change, which means your application must reconnect, and the JVM will cache that DNS forever unless you tell it not to. So set the TTL and test the failover before the night it happens. Automated backups give you point-in-time recovery, and they die with the instance. Manual snapshots survive it, so take one before anything risky. A restore creates an NEW endpoint, so your recovery time includes repointing everything, and your backups are not real until you have restored one. Parameter groups. Static parameters need a reboot, and the console will tell you it is applied when it does not. GP2 burst credits run out silently, and your database gets slow with nothing in your code having changed. Use GP3 and put a pooler in front, because your database can serve far fewer connections than your application would like to open. Next up, Aurora, and whether it is actually worth the money. Subscribe.